Hello, my name is Sydney Davis. I'm a fifth year electrical engineer in the BSMS program here at RIT, and I'm going to tell you about the CSTARS2 project. My work is a continuation of Ben Stewart and Kevin Gates, and I am advised by Dr. Doran Batru and Dr. Michael Zemkov. Lastly, this project is possible due to the continued financial support of RIT and NASA. And so without further ado, let me tell you a bit about the project. The CSTARS project supports another project here at RIT, the Cosmic Infrared Background Experiment, or CIBER for short. CIBER consists of a suite of image sensors launched as a scientific payload by a sounding rocket above Earth's upper atmosphere. During the approximately 10 minutes of the mission's active science phase, these image sensors capture infrared background radiation, which is simply another form of light, of spectral celestial targets. In order to stay on target, the sounding rocket is equipped with an attitude detection and control system located at one end of the payload and always looking sideways. This uses a star tracking algorithm to determine the orientation of the cyber payload and to keep it on target. However, since this system is located in a separate location as the cyber image sensors, this ADCS does not always account for the warping of the payload body caused by thermal deflection. This can be solved by installing a second ADCS, the unit that shares a focal plane with the cyber image sensor. In this way, the second ADCS will see the same star field as the primary cyber image sensors. Our ADCS unit is called the Cryogenic Star Tracking Attitude Regulation System, or CSTARS. In order to share the optical view with Cyber, we cannot include the power distribution or processing on the same PCB as our image sensor. Furthermore, similar to the Cyber image sensors, the CSTARS image sensor will also be exposed to cryogenic temperatures, and most electronics are not rated for such extreme temperatures. For these reasons, we have two PCBs, the focal plane board, or the cold board, and the interface board, or the warm board. While the cold board is located in a cryogenically cooled cryostat at approximately 77 degrees Kelvin, it sends its images to the warm board through manganene cables, and this board is located in a well-insulated section of the payload. The warm board also connects to the rocket's primary attitude detection and control system to report its orientation calculations, and it's connected to Cyber in order to receive mission status updates, such as when the rocket and payload are on target. The image sensor used in CSTARS2 project is the CIS2521F by Fairchild Imaging. It is manufactured using scientific CMOS semiconductor technology and uses 5 transistors per pixel. This allows the sensor to take clear images in noisy environments and offers the options of rolling shutter mode, which captures an image one row at a time and does not require much control, versus global shutter mode, which captures an image using every row at the same time but is more difficult to control. In order to track stars that are very far away, even the brightest stars are only a few pixels wide. And this is why it's very important to have low noise on every pixel, or else the inclusion of spontaneous fake stars would quickly confuse our star tracking algorithm. The image sensor needs a controller to operate correctly and to output images to. Not only do we want to perform star tracking on each image that's acquired, but we also want to save as many images as we can for post-launch analysis. For a device with many GPIO, or general purpose input and output pins, the ability to run two or more tasks concurrently, and as well as an easy way to save large amounts of data. To accomplish all this, we turn to AVNET's MicroZed development board, which includes a Xilinx Zinc 7000 series system on a chip. The microheaders on the bottom of the board, as seen in the lower image, have 100 pins each, providing us with more than enough GPIO to interface with the image sensor as well as some accompanying temperature sensors on the focal plane board. The Zinc 7000 also contains a dual-core processing system surrounded by programmable logic fabric, and this allows us to execute concurrent software routines within customized hardware. And lastly, It includes a micro SD card slot, which gives us a local location to store images while in flight. Now, to take advantage of the dual core processing system on the MicroZed, we dedicate the master core to starting up the system, and then it focuses on tracking and sending status updates to the attitude detection and control system. The slave core, on the other hand, once it is started by the master, is dedicated to saving images onto the SD card. Neither of these cores, if you'll note, focus on the acquisition of an image, because instead, this functionality is implemented in the hardware portion of the device. Because the procedure to acquire an image is so rigid and well defined, it is relatively easy to implement this process in hardware, and to start and stop the taking of an image with a simple flag from the processing systems. This ensures that the procedure is executed down to a clock cycle and cannot be interrupted by other processes. Furthermore, this removes some of the computational load from the processing system so that the two cores can focus on their respective tasks. The hardware description also allows us to form the necessary connections between the processing system and the peripherals, such as main memory and the SD card, which are then utilized by the two cores once connected. Now, before I joined the CSTARS project, the image sensor was being directly soldered to the cold board. This was done to ensure the connections between the sensor and the board were stronger than simply flexed metal prongs found in a common socket. In this state, the sensor and the PCB experienced several rounds of cryogenic testing, which involved cooling them both down to 77 degrees Kelvin and then allowing them to warm back up to room temperature. Eventually, after so many cycles, this caused the PCB to warp due to differences in thermal dissipation, and similar to the warping that would be expected in the sounding rocket. And so, as the PCB flexed, it actually ripped off some of the pin pads from the sensor, as shown in the upper right hand corner, and it rendered it unreliable for future testing. The previous team then concluded their work by designing a new focal plane board that included a socket instead of direct soldering. Although the flex metal prongs may be a concern during flight, a brief misconnection is not nearly as concerning as damaging the sensor should the PCB flex occur again. And in the new design, if it were to flex, this flexing would be experienced by the socket instead of the sensor. My summer started by populating this new PCB and by verifying all of its connections and installing a new image sensor into the socket. After populating the boards and safely powering on the entire system, we were able to acquire images from the image sensor semi-consistently. When successful, we were able to cover and expose various regions of the sensor. In the images shown, the bright white blocks referred to the presence of light, where the sensor is currently not covered, and the dark gray blocks referred to the absence of light, where the sensor is covered. We were able to create most of these patterns using masks, consisting of cardstock that was cut in specific places to allow light to shine through. Each of these images were then taken without an optical system present, which is an explanation as to why there are large gradients shown between the transitions from dark to bright. Now, each of these images have also been saved and loaded from the SD card to prove functionality that will be occurred during flight. And for debugging purposes, these images have also been streamed over a USB port to monitor the current images in real time. Tracking has not yet been attempted, and therefore the status messages sent to the ADCS have also not yet been verified for accuracy. Now, we have not yet moved on to tracking because we are not yet consistently acquiring images. There are times when the image sensor is powered on, and instead of lining up the columns in the order that we expect, each row seems to shift its columns by a few, resulting in slanted images. The top image was generated using a second FPGA connected to the same data pins that the sensor would be connected to. And this FPGA is producing a sample image such that it is supposed to have vertical black bars on the left and to the right, as well as a horizontal black bar on the top. Instead, as you can see, We see the vertical bars shifting from right to left as the image is processed from top to bottom. Furthermore, the start of this image, which should take place at the horizontal black bar, seems to be starting closer to the center of the image or is not consistent with the top. When this behavior is observed on the sensor by covering half of it, we see that an image with a black and white horizontal streaks, but they do not line up vertically, which leads us to believe that a number of the column and or rows are being reported as variable in length or size. Since this is working sometimes and not other instances, depending on when we program it or how it's booted, then this is not reliable for flight yet. And the arrangement of these rows and columns not being performed in a way that adapts to these changes leads us to believe that either we're not interpreting the images correctly or the sensor simply isn't producing constant images. And so our goal by the end of the summer is to fix the number of rows and columns being reported by the sensor until it is constant. Once we feel safe to proceed and we can trust the images being acquired, the next step for this coming fall semester is to apply the tracking algorithm while the sensor has an optical setup for focusing. If tracking is successful, then the status updates transmitted to the ADCS will be tested for accuracy. And then after that, the final step is to verify functionality at cryogenic temperatures. If all of this is successful, then the CSTARS2 project will officially be ready for integration into the Cyber 2 payload. For those of you who are curious, here are the references to the papers of my predecessors for the images and information that I've used to make a building block. And finally, I'd like to thank Dr. Doran Petru and Dr. Michael Zemkoff for their continued advice throughout my work on this project. I'd like to thank RIT and the Center for Detectors for providing me with the opportunity to work on this project. I'd like to thank NASA for their continued support of this project. And finally, I'd like to thank you for watching this video about the CSTARS 2 project. Thank you.